But it's going to be more than a talk about infinity and creating something that's larger than infinity, because the person that did this back in the late 1800s actually opened a door to a very big problem, which then opened another door, which opened another door. But we start with this little puzzle. Have you seen this before? I think I might be. It's zoomed in too much. And it's upside down. So, if you can see what it is, don't say. Does anybody know what it is? A black hole? No. Sasquatch? No.
Parabolic sunglasses?
Parabolic sunglasses? No.
Cloud?
A cloud? No, sorry.
A dog.
A dog? We're finally getting close.
Yeah, I see the eye. I see the nose.
What if I give the hint? Moo. Can you see it now? These are the two eyes. These are the two ears. Here's the nostrils.
Okay, I see it. See it?
It's a cow. Now this picture was given to me by a psychologist. She was talking about children with learning disabilities. It may be that you put the information out there and that's what it looks like to somebody. And you say, what? There's a cow. Can't you see a cow? So you're going to need to learn another way to teach the subject so that people can see, no, this isn't random information. Well, I steal it from her and put it in this talk because when you have a mathematical problem, as we sat there looking at this, is it really random information, or is there some type of pattern? Can our brain figure it out, or is it going to remain random information and we're not going to be able to figure out what it is? So, we start with an example from 1637. Fermat's last theorem from 1637. So you know, if you've got x squared plus y squared equals z squared, or a squared plus b squared equals c squared, that there are whole number answers for a, b, and c. For example, 3 squared plus 4 squared, do you know how much that equals? That's going to be a 9 and a 16, which is 25, so that's equal to 5 squared. And there's actually an infinite number of examples where you can have whole numbers, and it's going to be a solution to the Pythagorean theorem. Then, back in 1637, Fermat said, well, what if it wasn't squared? What if it was cubed? What if it was to the 4th or to the 5th or anything but squared? Then, for example, if you use the 5th, if you've got 2 to the 5th and 3 to the 5th, can z be a whole number, or does it have to be decimals? Can it be as nice and beautiful as this, just having 3s, 4s, and 5s? He said that he knew, but he didn't prove it. For the next several hundred years, nobody could prove it. Now here's an example that actually you could probably explain to a 7th or an 8th grader. And yet, all of the world's mathematicians couldn't solve the problem. In the year 1900, a mathematician by the name of David Hilbert, a German mathematician, went to this famous conference of mathematicians and said, you know what? We've got a bunch of problems that are laying around. They haven't been solved. They haven't been solved. What we need to do is we need to solve these problems. We can't just go on with our merry lives. We need to clean this up. So he proposed, there was 23 problems in his list, and he proposed that mathematicians get to work. Now this was in 1900, so Fermat's last theorem still hasn't been proved. Here's his list. The ones that are in green have been resolved. So I just took this off of Wikipedia this morning. The ones that are in yellow, I can See, so the dark green, those have been solved. The ones in yellow, partially solved. The ones in red, no, not at all. How many dark green ones are there? As a percentage? Not a lot. And that's been 112 years now. And keep in mind that some of these problems, if you were to solve, for example, P versus NP, some of these problems, you would win, if you could solve it, you would win the Millennium Prize, $1 million. So the motivation is there, but are we just not smart enough? Well, turns out that Andrew Wiles, a British mathematician, after 357 years, he finally solved Fermat's last theorem. And I don't, with this resolution, I don't think you can see it, but can anybody read that word right there? Hilbert. Hilbert, yep. So he was even using some of the math that Hilbert had invented in this talk right there. So it took him 357 years. So in other words, this problem of Fermat's last theorem, very easily stated. Is it impossible? No, it's possible to solve it, but it's very, very difficult. Take a look at, here's the first page of his proof. Modular elliptical curves and Fermat's last theorem. The introduction. An elliptical curve over Q, which means the rationals, fractions, is said to be modular. This is the way mathematicians make definitions. They say it is said to be modular if it has a finite covering by a modular curve of the form aleph naught over the n such that elliptical... I already got to stop right there and go get a dictionary. It's 100 pages long. That introduction, that's meant to be the easy part. That's just like speaking in plain English. Here you go, this is what we're going to be doing. We'll get down to the hard part in a second. So it took him 7 years of dedicated study. This was after he already had his PhD. 7 years of dedicated study to finally come up with this 100-page proof that yes, Fermat's last theorem is correct. If it's something bigger than a square, you're not going to have whole number answers. Okay, so it's possible that problems are very difficult to solve, but it is possible to solve them. Next, what about the prime numbers? So if you look at the prime numbers, 2, 3, 5, 7, 11, 13, etc., that's the building blocks of all arithmetic, which is then the building blocks of algebra, which is then the building block of calculus, etc. So we should be able to understand the primes very well. Is there a pattern? Is there some way that you could predict, okay, tell me what the 12,379th prime is? And you just push a button on a function and you go, oh, that's going to be this number right here. Again, mathematicians don't know. Personally, I don't believe that there would be a pattern to something as beautiful and so important as the primes, but that's just my opinion. So you could look at it a different way. Rather than looking at the list this way, just straight across, here's the numbers, maybe what you could do is try to look at it a different way. You highlight them. And maybe that those blue ones, which are the primes, I highlighted them in blue, maybe then seeing it that way, just like with the cow picture, maybe if you look at it in a different way, if you had some different information, you could see, aha, it's a pattern. It's making music, I can hear it. I know that song. Well, other people tried to prove that, yes, there is a pattern, no, there isn't a pattern. Related to that is the Riemann hypothesis. In 1859, now it's related to the patterns of the primes. It's not going to look like it, but it's related. So the Riemann hypothesis also was in that list of 23 problems that Hilbert said in 1900 we need to solve. The Riemann hypothesis to this day still hasn't been solved, but look at, it's a little more complicated than Fermat's as far as what does the problem say. Anybody that's had at least Math 3B would recognize this series right here. If you haven't, it just means add up these fractions. There's going to be an infinite number of them. It's going to be 1 over, and then you take 1, raise it to the p. And then 2, raise it to the p. That's going to be the second fraction, and then etc., etc. Just add those up. Now to make things a little more interesting, he said, with P being a complex number. All right, so right there, we're into definitely upper division math, not anything we do in calculus, definitely upper division math. And then he said, all of that is going to equal 0, so it will add up to 0 if, for the complex number, it starts with a half. For some reason, it has to start with a half. It can't be a third, it can't be a 7, it's got to be a half. Why a half? Nobody knows. It's again an unsolved problem. So, oh, by the way, if you were interested in winning that $1 million, here's the Millennium Prize problems. Rebound hypothesis, that's one of them. Oh, by the way, in one account I heard, if you go back to the first guy that actually did solve the problem, Andrew Wiles, in one account I read, he, in middle school, was told about the problem, started reading about it, and that's what inspired him to go and get his PhD. So it may be possible that today in this very room, by pointing these things out, I could be inspiring one of you, so see, to then someday solve the Riemann hypothesis. And if you do, when you get your $1 million, you remember who started you on that path, all right? So, so this, if we talk about the prime numbers, is there a pattern or are they random? This is a problem in computer science which says if you allow computers and they have, the programs that you write have to be deterministic. In other words, there's one step and the next step and they follow these logical steps and they're not allowed to do anything random. What if you then added one property and you call it NP, non-deterministic? What if you allowed it to use random information? So as the program is going through, and it decides, should I open that door or should I open that door? Rather than having some rule that tells it, oh, well, if you're standing on your right foot and your left hand's in the air, then you have to reach for it. No. What if instead you just use random information? You randomly tell it, open that door. The next time it asks, open that door. And it's just completely random. Is that random information going to give you more be able to prove more things with that? Another unsolved problem. So, what does all this have to do with infinity? So, Cantor was born in Russia, lived in Germany. In the 1880s, he started messing around with infinity. Other mathematicians said, don't do it. Don't do it. He said, I'm going to do what I want. They said, leave it alone, don't do it. Because, let's do a little bit of algebra. How much is 2x plus 3x?
5x.
It's 5x. How much is 7x divided by 7x? Is equal to 1. So we know these things about algebra. How much is 2 infinity plus 3 infinity? Is equal to infinity. That's true. Which then means it doesn't follow the rules of algebra. If it doesn't follow the rules of algebra, then it might possibly poison the well. It might possibly be that you end up proving things that are false. If you allow such crazy arithmetic that 2 of something plus 3 of something is equal to only 1 of something. Or over here, if you have 7 infinity over 7 infinity, then, do you know how much that is?
1.
It could equal 1. Now there's a couple of ways to talk about infinity. One is the way that we do in calculus, talking about limits. In that case, this can equal anything it wants to. It can equal 1, 0, infinity, it can equal anything. Or the way we're going to talk about it today is that it sets. You know, like a box of something with an infinite number of marbles in it. In that case, division doesn't really make sense. But anyway, when he opened the box of infinity, other mathematicians said, don't do it. He still did it. He also paid the price for doing it. He went to an insane asylum over and over and over again. Now, part of it is that he was bipolar, but yeah, that did have something to do with it. But anybody that has either a mental, emotional, or a physical disease can control or help control the problems by, if you're diabetic, then eat right and exercise and take this medication, and you can help yourself be healthy. He kept going back to this infinity problem, and it would drive him nuts. Okay, here's the first thing he did. The first thing is, we need to do a little bit of infinity arithmetic. So the idea of infinity is that you have the numbers 1, 2, 3, 4, 5, 6, 7, and it goes on forever. There's the idea of infinity. Also known as countable. In other words, can you count them? 1, 2, 3, 4, yes I can. So why is it that infinity plus infinity is equal to infinity? So infinity plus infinity means you have this plus itself. So that would be, I've got 1, 2, 3, 4, etc. And then I've got another 1, 2, 3, 4, etc. Is it possible to count that list? And it is. You just say, here's the first one in the list, the second one, the third one, the fourth one, the fifth one, the sixth one, the seventh one, the eighth one. And anytime you ask me, can you tell me what the eighth one is? I would go, 8 is 2 times 4. So I was in the second list, the fourth one over, that one right there, that's the eighth one. So for counting, you have to be able to, anytime someone says, hey, what is the 10th one? You have to be able to say, the 10th one would be right there. And then likewise, if somebody just randomly pointed to one, hey, which one was that? Oh, that's the third one. So, is it countable? Yes, that's how I can count it. 1, 2, 3, 4, 5, 6, 7, 8. So, infinity plus infinity is still countable. So that means that it's equal to what we typically think of as infinity. How about infinity times infinity? So in order to have infinity times infinity, I need a little picture like this. Well, if you have, for example, 3 times 3 in regular arithmetic, then, just like the way that I'm going to be teaching my son when he gets to be a little bit older, 3 times 3 means you've got 3 groups of 3. So here's one group of 3, here's another group of 3, and here's another group of 3. So 3 groups of 3 equals 9. You could do the same thing with infinity. You just need to have this go forever, have this go forever, have this go forever, etc. So infinity times infinity would look like 1, 2, 3, 4, 5, etc. 1, 2, 3, 4, 5, etc. And then you would just keep going down the list forever. So we'd keep going this way, etc. Can you count that? Well, if you start counting this way and you keep going, then you'd get stuck on that track and you'd never get to count the second line. So I could sort of do what I did in the other one. I could start counting on this one and then stop and go count on this one. And then I could count on this one, count on this one, and count on this one. And the way that it's done is beautiful. You count this one first, and then you count this one, and then this one, and you basically make a sort of like a snake is winding through, and you can create a function to do that. That means that you can count them, because eventually you'll get to each and every number. And so consequently, infinity times infinity is no bigger than just regular infinity. It's still countable. Do you know why the trigonometry teacher didn't have to go to the beach a lot? Because he had sine and cosine, so he could make a tan anytime he wanted. See, the little jokes can give you some time to push your brain back in your ear in case it's melting. So infinity times infinity, it's not any bigger. What then is bigger? What did he discover that's bigger? So here's what we do. First of all, the real numbers. Do you know what the real numbers are? It does include things that we can count. It includes positives and negatives, that's true. Decimals, that's true.
All real numbers?
It includes all real numbers.
Anything on a number line?
Anything on the real number line. So if you have 0, 1, 2, etc., -1, -2, etc., but you also include every decimal, every square root of something, every e to the something. If you include all of those numbers, those are the real numbers. They're actually divided into two types. There's the rational. Do you know what rational numbers are?
Right side is 0.
It's fractions. So this ratio means we're talking about fractions. So this would be things a over b. Or another way to do it is look at the decimal form. If you look at the decimal form, there will be either that the decimal form stops or it goes forever but makes a nice pattern. Like 0.123, 123, 123, 123, 2, 2, 3. A waltz, 1, 2, 3, 1, 2, 3. And then there's the irrationals. For the irrationals, then, well, ir is saying the opposite of, so it's the opposite of this idea. So it's not a fraction, and when you look at the decimal form, it does not make a pattern. So an irrational would be something like 3.14159, etc., etc. Do you know that number? Pi is irrational. There is no pattern. You can follow it out forever, and there is no pattern. So maybe these right here, these are countable. Because if you take infinity times infinity like I just did, and prove that that's countable, if you take infinity times infinity, well, how many a's are there? For fractions, you have to have everything, because sometimes it could be a 1 or a 2 or a 3 or a 4. So this could be representing the a's, and this could be representing the b's. And then that would take care of all a over b's, and so the rationals are countable. What about the irrationals? So what we do is take the numbers from 0 to 1. Take the numbers from 0 to 1, not including 0 and not including 1. Assume that that's countable. Assume that it's possible to make a list where there's the first one, the second one, etc. So the first one, so assume that this is countable. In other words, it's the same size as 1, 2, 3, 4, 5, 6, 7 forever. So if it's countable, then you can say, okay, give me the first one. The first one is 0.17346, etc. All right, give me the second one. It is 0.634871, etc. All right, give me the third one. And you keep going. And if they're countable, that list will count all of them. So eventually you would have every number on the list, if it's countable. Then here's what Cantor did. It's called the diagonalization argument. What he did is he said, look at the diagonal. This number, this number, this number. So you look at the first number for the first one, the second number for the second one, the third number for the third one, and now create a whole new number. Hey, in math, when you put a line over something, do you know what that means? It's what? It means the opposite. There are different meanings, but in set theory, it means the opposite. So that's what he did. He said, take the opposite, or in other words, anything but a 1. So make a 7. Then do the opposite of this. Do anything but a 3. Pick anything but a 3. All right, 4. Now pick anything but an 8. Okay, I'll put a 5. Is this number in the list? Well, if you counted all of the numbers, supposedly it's somewhere on the list. Is it the third number? It can't be the third number because this and this were made so they don't match. That means whatever you say, oh, it's going to be the 100th number in the list. I could go out here to the 100th digit, check with the 100th one right here, and they were made different. So this number, it's not on the list. Which means that when I assume this, you know what it did? Yeah. That means that these numbers between 0 and 1 are not countable. So we actually have something that's bigger than regular infinity. So if you go back to that the real numbers have the rationals and the irrationals, and we know that the rationals are countable, that means all of the irrationals in here are not countable. There's too many of them. And in fact, if you go to something called measure theory, which I'll just do briefly, the measure of the rationals in 0 to 1, in other words, not how many are there, but how much space does it take up? So this is an interval of length 1. How much space do the rationals take up? So yeah, there's a lot of them in there. There's an infinite number in there. But how much space do they take up? Are they fat? Are they skinny? What? They take up 0 space. If you then measure how much space the irrationals take up from 0 to 1, they take up 100% of the space. That is a lot more. That means if you were to reach in here and grab a number and you pull it out, it would be all crazy because it's going to be irrational. So he created not only something that isn't countable, but now, oh my God, how do we even understand that? Okay, so this is the can of worms that he opened. We've got a set that's not countable. So this right here, you could also do in binary. What's binary? Using only zeros and ones. If you use only zeros and ones, then there's 2 possibilities for this, either 0 or 1. There's 2 possibilities for this. There's 2 possibilities for this. 2 possibilities for this. And if you have 2 times 2 times 2 times 2 times 2 times 2 times 2 to count how many possibilities are there, you will get 2 times 2 times 2 times 2 times 2, 2 to the infinity. So it turns out that infinity squared equals infinity. 2 times infinity equals infinity. But if you've got an exponential function, 2 raised to the infinity, then that is definitely bigger than just regular infinity. Mathematicians of the time did not want to believe it. They called him names. They said he was crazy. Okay, maybe he was, but the math wasn't. So, like I said, this talk is going to create something bigger than infinity, but it's a much more important story than that. Because then he said, all right, when we're talking about real numbers, I've got a 5 is smaller than a 7. Got a 5 smaller than a 7. So if a 5 is smaller than a 7, is it possible to have something in between? Does anybody know a number in between? A 6, or a 6.3, or a 6.9, or a 5.1. There's a whole bunch of possibilities. Okay, that's pretty obvious. If 2 things aren't equal to each other, there's going to be something in between. Then what he said is, what's in between these two? Is there something that's between regular infinity and the uncountable infinity? This is what sent him to the asylum. He would work and work and work. He thought that he proved it. Yes, there is something in between there. And he would send his work off to like one of the famous math magazines or publications. And a week later, he would write back and say, no, don't publish it. It's wrong. I found a mistake. In fact, I don't think it is true. I think there's nothing in between. And a week later, he would write back, no, I proved it. There is something in between. No, there's not. This is called the continuum hypothesis. This is called the continuum hypothesis. If this is regular infinity and this is uncountable infinity, is there anything in between? So he worked and worked and worked. He was never able to prove it. And to this day, nobody's been able to prove it. So, is it a problem like the first one that's just going to take 357 years until somebody can figure out how to solve it? Or is it some new creature completely different than we've ever had before? Is it something that actually can't be proved? Is it something that when you ask God, is it true or is it false? He's like, yeah. And you're like, I didn't get that. Was it yeah or yeah? Yeah. Is it true or is it false? So this idea that there could be something that is neither true or false is something that had never happened in math before. It then took until 1931 when, do you know which one is Kurt? A good friend of Einstein's. I heard a quote from Einstein in his biography that I just started reading. He said, well, I'm not going to quote, but his idea was, the only reason that I really like to work at this place is because each evening I get to walk home with Kurt Gödel. That was his best part of the day, he said. So this guy was brilliant. Here's what he proves in 1931. Mathematicians work with axioms. These are basic rules. In fact, you know a lot of the axioms of arithmetic already, like how much is 2 plus 3 equal to 3 plus 2? That seems to be true, right? So these are basic rules, properties that we know from arithmetic. Do you know the name of this one? When you switch the order and get the same answer? What is it? Commutative property. They're commuting. Or how much is 1 times 7? That's equal to 7. Or how much is 1/5 times 5? Equals 1. The basic rules of arithmetic. There's about 10 of them. Now when you go to each area of math, they have their own rules. So for example, in set theory, they've got 10 rules. Arithmetic, there's about 10 rules. You go to topology, they've got their own rules. There's the basic ones. And then they say, from those basic rules, they're called axioms. From those axioms, we will build up everything. Everything has to be proved from the axioms. So, you can prove things like 1 plus 1 equals 2. Have you ever seen the proof for that? I can't remember now, but it takes something like hundreds of pages to prove 1 plus 1 equals 2. So anyway, we build up from the axioms. And what Gödel proved In 1931, he said, if you have a system, whether you're in topology or building up from algebra, from arithmetic to algebra to calculus, etc., if you have your system and it's complicated enough that it can do the rules of arithmetic, so if your system is strong enough that it can do 1 + 2 = 3 and things like that, here's what's going to happen. There's going to be something out there you can't prove. So if you have 10 axioms, eventually somewhere there's going to be something that cannot be proved, which mathematicians really didn't like because they wanted to be able to prove everything. What Hilbert was saying back in the 1900s, he was saying, you know what? We are too sloppy and lazy to have these unsolved problems just sitting around. We should be able to prove them. It turns out, though, there are ideas that can't be proved with the axioms that you have. So, actually at the time, set theory had 9 axioms. So the set theorists fought with each other because when you add an axiom in, you're changing all of the rules. And it's possible you could accidentally put one in that poisons everything. You didn't know it at the time, but you're like, yeah, I got this new rule, 7 + 2 = 11 from my cousin, and we're going to start using that from now on. No. So mathematicians are very, very sensitive about adding new things in. But they were actually, with the work of Gödel in 1931, yeah, the second incompleteness theorem, he did 2 famous theorems in 1931. So with his other one, he proved half of it. Oh, it was 1938. So anyway, he proved you can't prove this false. Doesn't mean it's true. He's just said with the axioms that we have so far, you can't prove this is false. Then in 1963, a set theorist, Paul Cohen, he proved you can't prove it's true. So in other words, with the axioms that they had, you can't prove it's true, you can't prove it's false. You just can't prove it. So no wonder Cantor couldn't figure this out. It was not possible. Which then means a few things. You have 9 axioms. You add in a 10th one thinking, oh, now we'll be able to prove this one. The 10th one, even with the 10th one, they're not able to prove this. That means they're going to need an 11th one. The set theorists in the last decade, they're still fighting about it. In 1999, 2002, and 2003, a set theorist by the name of Wooden said, hey, I found it. Here's the new axiom that we need. And then we could prove that this is actually false, that there's nothing in between the two. But the rest of the mathematicians and set theorists haven't accepted it yet. This idea applies to other fields. Think about physics. In physics, they've got a finite number of rules. They then try to explain how does the world work with these finite number of rules. Then they come along with some other physicists, discover something and says, hey, look at this. This doesn't seem to fit any of our rules. And they're like, oh, that's okay. We'll just invent quantum theory. All right, now that we've got quantum theory, we're going to be able to prove everything with a finite number of rules. And then somebody comes up with something else and they go, okay, well, we're going to invent quarks right now. And then something else comes up and okay, we're going to invent string theory there. And then put all that together. All right, and then something else comes along. Okay, well, we're going to do superstring theory. All right, and that didn't quite do it. And then, but the physicists keep thinking, yes, it's possible with a finite number of rules that they could prove everything. And I'm going, dude, Gödel in 1931 said you can't prove everything with a finite number of rules. He proved it a long time ago. The physicists don't listen to me. They don't listen.
If infinity is real, shouldn't there be an infinity amount of axioms?
What's that?
If infinity is real, shouldn't there be an infinity amount of axioms?
Right, that's basically what he's then saying, because you would always need one more axiom. So you get to 11 axioms, and then somebody's going to find something that's outside of that realm, and you go, okay, one more axiom, one more, and you would need an infinite number of axioms. That's true. Does anybody else have questions or comments? All right. So, did I finish that? Oh yeah. So it was in 2001, 2002, the set theorists said, okay, well, if we adopt this extra axiom, then we're going to be able to prove that the continuum hypothesis is false. But they haven't yet decided to accept it. One more thing about the physicists. So here's a paper that I found in looking at this. Gödel and the End of Physics. And I was like, oh, some mathematician finally listened to what I was saying. Some mathematician's going to take them down. I got to read this paper.
We have a physics club here. To welcome them.
Okay. And I would like to welcome this physicist. Have you ever heard of Stephen Hawking? Is that a yes or no?
Yes.
Okay, you don't need a picture?
No.
It's amazing that Stephen Hawking is still alive. He's what, 75 now? They expected that he might have lived until his 30s. He's like in his 70s now. So, what did Hawking have to say about my idea? I mean, the idea? So here's the conclusion. But then, with our experience with supergravity and string theory, so that's what I was saying, they add on more and more things. With our experience with that and the analogy of Gödel's theorem, suggests that even this formulation is going to be incomplete. So some people will be very disappointed that there's not an ultimate theory. Something that Einstein was looking for, something that physicists have been looking for and looking for. That cannot be formulated in a finite number of principles. I used to belong to that camp, but I've changed my mind. I'm now glad to see that our search for understanding will never come to an end, and that we will always have the challenge of new discovery. Without it, we would stagnate. Gödel's theorem ensured there will always be a job for mathematicians, and then because he is a mathematician, I mean, Gödel was a mathematician, he's then, what Hawking is then saying is, well, we need something like that. There's got to be something like that in physics, and he thinks that M theory is going to do the same thing. So that's about it. Does anybody have any questions?